to Carly. She is a developer advocate at Elastic. She's based in London. She spent over 10 years working as a technologist at a large investment bank, specialising in front-end web development and agility. She is a UI developer, visualisation geek, and regular blogger. She lives in London with a 4-year-old and is almost never far from a trusty cup of tea.
It's right
there. So without further ado, I will hand over to Carly for her talk. Please give her a warm welcome.
Thank you, Becky. Hello, everyone. Happy Saturday. I see we've all got coffee and teacups. That's great. So, as Becky said, my name is Carly. So I work at Elastic. So I know a little bit about search, not just working at Elastic, but it was actually my master's thesis topic as well. And today I'm going to talk about vector hybrid search. So what we're going to talk about today is what the difference is between these two things. Kind of showing the evolution of search and how things have changed from not just Archie, which was considered the first internet search engine written in 1990. That is not why I named my son Archie, just a disclaimer. So we're going to talk about the evolution of search and use Elasticsearch to dive into the fundamentals. So this is about trying to learn how these search technologies work under the covers so that you can figure out which is the right option for whichever search solution you're building. And then we'll have time at the end for any questions, so feel free to send those through. Otherwise, you can catch me on X, I'm on Mastodon, LinkedIn, all over the place, or come and find me afterwards. I don't bite, honestly. So, as I said, we're talking about keyword and vector search. We're talking about combining them together. And then we're also going to briefly touch on large language models because, well, it would be rude not to talk about some form of ChatGPT in a vector search talk. So, just a quick show of hands for me. Who has heard of Elasticsearch? Great, cool. So bonus question, who has heard of Lucene? Okay, so not the same number, but I'll forgive you, it's okay. So for those who haven't, Elasticsearch is a distributed search technology that you can use to perform performance search. And the way that it works is it actually uses Apache Lucene, which is an open source text and now vector search capability. And it takes those and it distributes it across multiple nodes so that you can search over a large number of documents in a performant way. So we've got to talk about keyword search because that's how we used to search for things and still do. Thinking about, again, Archie, the search engine, and then moving on to talking about, emergence of Google through the 90s and beyond. This is how we're used to searching for data. But how many of us really know how that works under the covers? So that's what we're going to talk about now. So what we have, think about the web, think about any document corpus, set of documents that you have. You will have a set of those that basically undergo a translation, which ends up resulting in what we call an inverted index. So this index is just like the index at the back of a book. It's basically got the list of terms from each of my documents, and it tells me which document that particular term exists in, but then it also might tell me the position. And in terms of talking about how we get from this document to this set of terms, we really need to extract what's called the tokens. So in simple terms, the words of interest that we actually might want to search over. Because in order to make search performant, we search over the inverted index. Can you imagine how long it's going to take if you're searching for one term on every single document in even hundreds of document corpus? It's going to take a while. So there's three main stages that you need to think about. So the first is stripping out any unused characters. So if I take this document excerpt as an example, you'll see in really small terms that it's got HTML tags in it. Are we really going to search for HTML tags? No. So we'll strip those out. Then we split them into individual tokens. So normally a tokenizer, you need one tokenizer in order to actually split things into terms. We'll basically take things and split it normally by punctuation and spaces, thinking about the traditional English language. And then finally, we'll do additional filtering onto the tokens to try and remove tokens we're not interested in, perhaps try and remove any other redundancies to prevent partial duplicates, all those kinds of things. So have I got any Star Wars fans in the room? There's less Star Wars fans than know about Elasticsearch. I'm really surprised. That's not how I thought this was going to go. Okay, that's cool. So for those in the room who are Star Wars fans, or maybe have seen even remember. Can anyone remember what Obi-Wan wisely says at this point in time? These are not the droids you're looking for. Thank you. So let's take this example and show this tokenization in action, okay? So these are not the droids you're looking for, emphasizing not. So I'm using the Analyze API here in Elasticsearch just to simulate that tokenization process we just walked through. So you'll see I've got character filter, so I'm going to strip out the HTML because I'm not going to look for an M tag. And I don't know many people that would. I'm just using a standard tokenizer because I'm using English text. It's probably going to work just fine. I don't need to think about other language considerations. And then for my token filters, I'm going to convert everything to lowercase because obviously that is a great way for handling, you don't want to have the with a capital and small in your index. That's just, you're not going to be able to join things together. And then we also have stop, so I'm removing stop words, and the, probably not very interesting for querying. And then I'm making use of a snowball stemmer to basically take any words that I can cut back to the original logical root. And through this, I've got 3 tokens. So I've got droid, which kind of makes sense. I've got U, so it took UR and cut it down to the logical root, which allows us to remove like UR and any other kind of duplicates on top. And the same thing, looking, looked, etc. will all resolve down to look. So expanding on the Star Wars example, which is going to run through the entire talk, let's take an example document and then show how we can search and understand the limitations of keyword search. So I've got an example document. I basically took all the Star Wars films and the list of Star Wars films articles from Wikipedia for this example. And I actually used the web crawler from Elastic quickly to pull out the content. But there's no reason you can't write your own. Has anyone written their own web crawler out of curiosity? Cool. So you can use that now to take out the document set and try this out. Cool. So what you have basically here, whenever we search for this document and find it, it will be present within an index. I've got a unique identifier. I've got the score. So when searching, obviously, how relevant is this particular document to my query? And then the source is actually the original document source. So you'll see body content is basically the whole content. You'll see I've got my domains, my title, my URL. So kind of useful things for a web page. So if I was searching and I wanted to find the latest Star Wars film for the people in the room who are not Star Wars fans, one might logically think, well, what about if I just look for the latest Star Wars film? So this is the most simple keyword search you can do. Basically as a match, and it will look for this term within the body content. Now, this is the first result that I get back. Is this correct? No, it is not. And I'm not just talking about, there's the alternative order of how you watch these films, or some people that wish that Jar Jar didn't exist and episodes 1 to 3 should disappear. But that's not what I'm talking about. This is the second film within the original 3-part series. So it is not the latest film by date or any other consideration. And that's because with keyword search, we're looking for exact matches within the text, which normally works great, but it doesn't pick up the idea of semantic context. It's also really difficult to try and deal with vocabulary mismatch. So that idea where I might use one particular word or phrase to refer to something, and you might use something else to refer to the exact same thing. So semantic search is what's appearing, if anyone's used Google recently and seen like the new semantic pop-up answers or even ChatGPT, this is where vector search comes into play. So if you've ever wondered roughly how that kind of idea of comparison works, that's what we're going to talk about through now. So we need to understand what a vector is and think back to high school mathematics, which for some might be quite a pleasant experience. For some, I'm sorry if it was not so great. But using a simple idea of bag of words, which is where I just simply count the number of occurrences of each of these terms in my 2 documents, we're just talking about a simple representation in space on multiple dimensions, okay? And then the way that vector search is that you take documents, and this is the other advantage, documents of different types. So obviously logically thinking about keyword search, you're looking for textual terms in a document. Trying then to try and adapt to images and audio is a little bit more tricky. So if we can just do some way of translating any form of document type into a vector and do the same thing with our query on the other side, we can then perform a nearest neighbor algorithm to try and pick up the results that we want, okay? So how does this work? Well, it's all to do with graphs and graph algorithms. So again, apologies to anyone thinking back to Dijkstra's algorithm and all those scary things for anyone from a computer science background. But the idea is that you have a vector representation of your query and you're needing to perform distance calculations across the graph to find the closest documents. That's how this algorithm's working. And there's various different types of algorithms, but ultimately, if you're looking across an entire graph space, that's quite an expensive thing to do. So one way, and one up-to-date algorithm, which is actually one used within Elasticsearch and in Lucene under the covers, is hierarchical navigable small worlds. Say that 3 times fast. Try again after you've had a beer as well. That might be tricky. But basically the idea is it splits into layers, and then we're performing these kind of comparisons on each layer and use that to find a set of results by distributing the problem. Now that obviously leads to a potential balance on accuracy, because you might not look at every single candidate within each layer, but it allows us to split out the problem. And in fact, there's all sorts of new algorithms appearing all the time. So an example I saw recently was DiskANN, which is meant to be a single layer approach. So I haven't dug into it in the details, but it's something that's changing all the time and is something that's adopted by different vector search databases. So it's worth having a look at. But to look at an example, more Star Wars, if I think about the idea of if I wanted to look for cartoon Obi-Wan, or maybe Obi-Wan from the Clone Wars cartoons, what you'll end up seeing is thinking logically, if I want to pick the 2 closest candidates, it's going to be these 2 here. So this is my obviously exact match. We can see that looking at the semantic context. But Wally was in this was Wally rather than Star Wars, so obviously it doesn't quite. It's a consideration of picking the number of candidates, okay? So another question, who's from a machine learning background? Okay, so you're all the people that are going to keep me right when I talk about models, okay? Because as I said, I am not from a machine learning background. As I said in my intro, I'm from a software development background. But that therefore means that I kind of understand the scary fear whenever someone says machine learning models to others in the room they're not familiar. So a model in very simple terms is basically a black box construct that has been trained on a document and classified label set, as covered in the talk earlier before the break when we talked about the phishing emails. That was a labeled set of data, and we talked about how the labels were captured. And basically what we do is we use that classified set of data to train that algorithm to make the decisions of how to get to that result, i.e. the labeled result. And then we use it on something that it's not been trained on to try and evaluate and figure out what's going on. And this is where it gets even more scary, because there's all sorts of different models, and it really depends ultimately on the task that you're trying to do. So the model type that we're going to talk about today when we talk about models is text embedding. It's that idea of taking that textual image, whatever it is, document, and and then changing it into a vector representation. But there's other ones that you might use on the top. For example, if you have a vectorized document set, and you then want to engage and start asking questions and answers of it, you might end up using a subsequent question answering model on the top. So there are 2 ways in Elasticsearch to generate vectors. One is paid for, one is not, and I'm going to walk through both. So this is the platinum option, and what this is basically you basically import a particular model into Elasticsearch, and then you can use it with an ingest pipeline to run through and generate the vectors for you. So I've just picked a model from Hugging Face. I've used Eland, which is called the Data Science and Python Machine Learning client from Elastic that you can use for flipping through on data frames and also for importing models critically. So here I'm specifying my settings for my Elastic cluster, the model ID that I want to send in, and the task type I've set as test embedding. And this will be basically compatible for any PyTorch compatible model. And then, as you can see here, I can then simulate it and see what vector representation, validate that this is actually doing what I thought it was going to do. Then to generate the embeddings, I created what's called an ingest pipeline, which basically allows you to take a set of documents and perform various different transformations and enrichments on the top. I'm re-indexing it, so I'm taking this search Star Wars films index and then creating a new index, applying that pipeline onto the documents in that index. And then I end up with an enriched document that includes this text embedding predicted value characteristic here, which is my vector. Now, in practice, your vector is never going to fit on a widget this size. I've cut it down for illustration, but you get the idea. That's where your vector is coming from. The second way is to generate your own embeddings and then simply ingest it into Elasticsearch, because the bit that's actually, you can use irrespectively is the KNN search algorithm. So the way that you can do that is you basically have a model. So I've got an example code snippet here written in Python, and I am using the inference API from Hugging Face. So normally in practice, you might either have, your model running with Hugging Face and making use of the paid feature, but I wanted to try and find a free way to do it. So either you can download the model and then run it within your own ecosystem, which would probably be the better practice, or alternatively, they have a free kind of rate-limited API that you can use just to try something out, which is what I've done here. Sorry? Oh, that's okay. Cool. So taking your token, so register for account with Hugging Face, generate the token. Then what you do is you initiate a post request against that API, specifying the model that you want to actually generate the embeddings for. And then that's going to give you that vector representation back, which you then basically do an index using the Elasticsearch client in order to generate the result and index that document into your inverted index. So this is where it also kind of got scary for me. I'm still learning as I go, so I wasn't quite sure what models to use, how to evaluate and compare one model over the other. And there's obviously experts in the room that might have a better idea of how to go about that. But my general experience is starting off with one from an open source repository, such as Hugging Face, or making use of Clip. Or my colleague Alex recently did stuff on audio files using Pan's inference library, which is actually quite cool. His blog is there. If anyone wants the direct link, I can give it afterwards. Try those out to start with, see what results you're getting. And then if that's not quite working out, then we start trying to expand either by using hybrid scoring, if you feel that keyword search combined with vector is the right way to go for you. And we'll talk about why you might want to do that in a minute. Or alternatively, you can bring your own model here, which obviously requires the expertise of the lovely machine learning experts in the room and a trained data set. Sorry, a labeled data set. So the way that vector search work is there's an inference API, exactly the same as we were talking about with Hugging Face, okay? And what you basically do is you have the indices that are containing your data that contain that embedded vector, and then you're going to apply to your query that comes in the exact same inference on the top, and then the KNN search is going to kick in and find all those results. So this is an example where you generate it using the embedded model. So going back to that Platinum idea, where basically I'm still using the same search keyword. So anyone who's familiar with Elasticsearch will know about the search endpoint. But I specify a KNN rather than a query. I specify the field where my vector resides that I want to do the comparison. I specify K. K is the number of results, neighbors that we want to find with that KNN algorithm. Then the number of candidates is the number of candidates that are evaluated in each shard. So remember we talked about this idea that Elasticsearch is distributed across basically the way it works is you take your query, you have all your documents kind of distributed across multiple shards, it will send out the query to each shard, and it will evaluate this number of candidates on each shard to find the closest results, then merge them back together on the master, and then it will cut down to the final top list of ranked candidates. Does that make sense? Cool. I'll take nods as good. And then, as you say, if you've got the embedded model, you specify the model ID, the text that you're wanting to actually, query against, and the vector builder will generate the embedding. But alternatively, you're just going to pass it in directly with query vector. So this would be the case if you've generated the embeddings outside. You would generate the embedding outside for that query, and then you would submit it in. And then this is a result that we get back. Do you think this answers my question about the latest Star Wars film? No? Oh, interesting. Who thinks it doesn't? Yeah, and you go.
It's not the latest, it is a list.
It's not, but it's a list of all the films.
But you want the latest.
I do. This is interesting because this is up to interpretation. We could have an interesting discussion on this later. Because I would say it does, purely because the answer is in there. But you're right, it is not the page that we're looking for, which would be this one. So, considerations, so comparing vector search and keyword, well, we've got to think about the fact that vector search, we're doing mathematical calculations, it requires a lot more memory. Indexing is slower because we're performing that generation of those vectors is the second problem. And then merging is an interesting thing. So if you add another document, that generates a new segment, thinking about that graph. So sometimes you need to kind of merge and squish things back together, because obviously the more segments you have, then that means that the more kind of distributed, the larger number of basically segments you're having to compare over. So best practices, aware it's not always possible, try and avoid searches when you're indexing and adding new documents in where you can. There is the option to use something called synthetic source in this case to exclude the vectors from the source itself. Reducing the number of dimensions, so by default, Lucene, and therefore Elasticsearch, supports dimensional vectors of 2048 dimensions. You don't necessarily need all of that. Even ChatGPT doesn't use 2048 dimensions. And then finally, to decrease the precision, you can use a byte representation rather than a float for your vector, and there's supported types for each. So how do we stick this together? Because think about it, if I do a vector search and I also do a keyword search, I've got two different data sets. So how do I marry them together in a way that makes sense? And this is something that historically you kind of have to rely on a bit of kind of experimentation. In fact, if anyone was here in May, there was a great talk by Trustpilot where they talked about exactly that, combining different rankings together and their experimentation approach to try and figure out what their boosting factors should be. I'm seeing some nodding heads. It was good, cool. So what we need to do is we need to find a way to combine these scores together. And there's two ways that you can do it. There's either linear combination, which is exactly this example we were talking about with Trustpilot, that idea of specifying the boost factors, comparing the queries with the results, and then seeing if they're in line with what you expect. Or alternatively, there is a blending algorithm that's called reciprocal rank fusion, which can blend through, and we'll talk through both of these now. So this is how you would do the boosting, okay? So you'll see that I've got two types of query. I've got the latest Star Wars keyword query from before, and then I've got my KNN query here together. And what I've done is I've applied a boost to each of them. So what this is going to do is it's going to take basically the score for all the documents in this particular query here, for example, and we'll basically boost it by adding a factor of 0.4 on the top, okay? And then obviously KNN is having a higher boost on the top. In terms of trying to find out the right value for this, it is very much experimentation. It is trying loads of random values, going about it in a very experimental way and trying to figure out which results are right for your use case. But the other thing is, we could make this as complicated as we want. We could have multiple dimensions that we've generated vectors for, hypothetically. So, for example, I might want to have a particular comparison on a title that I've generated into a vector, and then on the original text embedding for the body content of my particular Wikipedia article. And then I might want to also apply it to a vanilla keyword as well. So you can make this as simple or as complicated as you like. The point is that you will be specifying your boosts for each of these. But otherwise, you can try what's called reciprocal rank fusion, which is this lovely algorithm here. So basically what it does is for every single kind of set of documents in each query that you have, it's blending them together using an aggregate and including what's called K, which is a factor for kind of blending together. And the default typically set, looking at journals, but also within Elasticsearch, is value is going to be 60 by default, okay? D is obviously the set of documents, and then R is the rankings for each one from each of the queries I've got, okay? So for example, if I had 2 algorithms here and these were my results, basically I would aggregate the results together and then potentially, if I step back, and you can't hear, oh, there we go. Step back, you'll see that the document is in fact reordered into a more blended approach. So it doesn't match either, but it's kind of a happy middle. Now, this is where it gets interesting, because I said, didn't I, that you don't need to specify factors and go through this experimental approach. But then you're wondering, well, why have you specified 2 parameters here? So the way to do reciprocal rank fusion is still technical preview in Elastic as of 8.10, but the theory is still the same. So the idea is that there are defaults set. So there's a default window size. So by window size, I mean the number of document results for each algorithm. That's how many you're going to evaluate. So similar to that idea we talked about with number of candidates, this is the number of documents that you're going to evaluate for each of those ranking algorithms. Okay? And then the rank constant is that K factor that we talked about before. You don't need to specify these if you don't want to. The best advice I would give is try and start with the defaults, which are for window size 100 and for rank constant 60, and then make sure that that's in line with what you want. And if not, to be perfectly honest, try out some other experimentation. But the point is that you can still try out a default first, see if that works for you, and then start kind of going down the rabbit hole of experimentation. So I promised a bit of ChatGPT. So one of the things you have to think about with ChatGPT is that depending on the licensing and the version of ChatGPT you're using, there is licensing considerations, and there's also considerations about your data. So it might be a case that for proprietary information, you don't necessarily want ChatGPT to be trained on top of that. Yeah, we're seeing some nods. And in this case, you potentially would want to leverage a large language model that you select that's within the terms and has been trained on perhaps a data set that you're comfortable with and that you can also bring in-house. And certainly, I will wander over here so people can see the QR code, but there's an article in here. So the idea is basically if you leverage Python, either a Flask application or whatever, to basically perform the initial vector searches and then bring those results in. You can then send them out to either OpenAI or whichever large language model you want to generate off the back of that subset of documents exactly what the response would be. And as I said, if anyone wants to read the detail of how this is done, I would recommend having a look at that blog post in the QR code as well. So, which large language model to choose? Again, I said I'm not an ML expert. This picture sums it up. So that resource there is a different QR code, actually, and it takes you to the LLMs practical guide on GitHub, which is this fantastic resource compiled together, which has some great ideas of what to learn about, talks about the different models, but this image is actually taken from there. And you can see that after basically mid-2021, it's all gotten a bit nuts. When picking a model, there's all sorts of things you need to think about. You need to think about the repository. You need to think about the licensing terms. You need to think about, are there any maybe code of conducts for responsible AI, such as the one from Meta for Llama 2, that you need to take into consideration. And you also need to find out if they're going to be trained on your algorithm as well. So I recommend having a read on that practical guide, looking through carefully, making sure you're happy that the model you pick is the right one for you. Now, we've talked about a lot of things today. We've talked about keyword search, we've talked about vector search, we've talked about how they differ, and we've talked about the theory underneath. We've talked about how you can combine them together because it's not always the right situation to prefer one over the other. If you've got a direct match, stick with keyword. If you want to combine together with semantic capabilities, you can absolutely do that. And then we also talked briefly about large language models with some advice on how to pick them and how to integrate it with your own private data. So I want to say thank you. We should have time for questions. Otherwise, the mic will get passed around. If not, feel free to come and find me afterwards. I'm always happy to chat.
Amazing, that was fab. Thank you, Carly. Have we got any questions? I'll come over. When you're talking, if you talk right into the mic, I think you need to hold it quite close.
Thanks. Great talk. So there's a bunch of vector databases now out in the world.
Yes.
And one thing I've seen from them is that they're quite performant.
Yeah.
There's other, Lucene has vector search.
Yes.
PG Vector has it, but these are not as performant as these bespoke databases.
Yeah,
is
fair.
this something you guys are looking into, increasing performance actively right now?
It's not just us, it's the Lucene community. So Lucene's an open source project,
Yeah.
and certainly there's been regular contributions coming in. In fact, in June, there was one community contribution that was made. They made an optimization to the number of comparisons. So it is something that's changing all the time. I mean, you're absolutely right. There's different vector database solutions. They've all got different algorithms, different approaches. Actually, I'd pulled this up because I expected this question was coming. If you're interested in basically vector database comparisons, my honest opinion is take a check of the benchmarks. Make sure it fits your use case, make sure it fits what you're wanting to do, and is it the performance grade? Because in terms of Elasticsearch, the last time I checked the benchmarks, we were kind of pretty much in the middle, as you're kind of pointing out. But obviously, it depends on what you're trying to do. It depends if you're wanting to combine the cases as well. So what I'd recommend is basically looking at Eric Ben's AMM benchmarks. These are run regularly. It's something that's community maintained. Elasticsearch and a lot of other major vector databases are in there, and it allows you to get a reasonable vendor independent comparison as well. Because I think Zilla's have their own benchmarking tool as well that they've been pushing out, but obviously they've got their own vector database as well. So
Yes.
I've
seen QDrons as well, and it's
Yes.
not independent, but yeah, it's interesting.
Yeah, no, totally. It's all about looking at the benchmarks. So, but that's a really fab question. Thank you.
Any other?
Hi, thank you very much for the talk. I was wondering, first of all, how do you do this hybrid? If there is the result from semantic search and exact match, is there some algorithms, or do you just let LLM to do the hybrid? And my second question is, sorry, maybe just one. Yeah.
We can come back if you've got another one that pops in. So the way that you do hybrid, let me flip back a few slides. If I go back to the individual one. So that's where this you're basically having to blend the results, and there's two approaches. So there we go. Either what you're doing is basically you take each of the particular queries that you have, so irrespective of whether it's a semantic search result, which is giving you back a list of documents that match in terms of proximity, and then you have another algorithm which has got your kind of keyword ones that have been done by direct matches. What it does is you either do linear combination, which is basically you say, right, okay, so for this query here, I am going to have a boosting factor. So each of these results will have a higher boost by maybe 1, whatever the number is. And then this one is boosted by a smaller factor. And then the idea is that when the results come together, it's just direct score comparison. So it's just saying, well, this one has a score of 10, this one in this set has a score of 20, so therefore this one will be higher in the combined set. Meanwhile, if you talk about reciprocal rank fusion, it's more of a blend, so it's meant to try and kind of blend together with an equal balance trade-off rather than manually kind of taking a stronger preference of one over the other. So it's meant to be more of a kind of natural balanced approach. So that's the two main ways that you can combine the different sets together. Does that answer your question?
Yeah, amazing. So that's where my second question comes in. How do you I'm curious about the matrix of measuring the score. Do you use TopK or something like that?
In terms of benchmarks for Elasticsearch, you mean?
Yeah.
So we do have a set of benchmarks that we run regularly on Elasticsearch. There's also the ANN benchmarks there that's more specific to approximate nearest neighbour. But we do have our own set of benchmarks that we publish regularly. So we do, as part of every release regularly, there is ongoing kind of regression testing against data sets to compare. So, the algorithm used in both Lucene and Elasticsearch, therefore, is BM25. So it's basically taking a document set, and then we run basic benchmarks and results, precision recall, all sorts of other things on that to basically see where things are, and that's done as part of kind of regular releases all the time. Does that make sense?
Yeah, thank you very much. If you can talk more about that.
Yeah, sounds great.
Any more questions?
Hello, thank you very much for the talk.
Thank you.
I had a question about this hybrid thing as well. So I was wondering if it's possible to provide my own function, for example, or even a model to kind of balance this if I want to do it somehow differently.
So like a custom score.
Yeah, maybe like custom, maybe not like a constant score, but maybe some kind of a model incorporate there to have my own like blending between two different things.
So I'd need to check, because I haven't checked for the KNN, I'll be honest, but with traditional keyword, there's a construct called a script score, and what you do is you can write your own function. It's normally written using Painless, so it's not like bringing in your own model, but you can write your own kind of script score to say, look, this is how I want to calculate the score for my document, and it's a custom implementation that you have obviously would need to maintain. But that is one way to do it for traditional keyword. I'll be honest, I'd need to double check and confirm if you can do the same thing on the KNN endpoint. But I'm happy to take that offline and check if that makes sense. But yeah, a custom script score written in Painless would be the way to do it.
Thank you.
Thank you for the chat. Actually, building on what she just asked, like there are plugins that can allow you to do NTR models, learning to rank models within Elasticsearch.
Cool.
So, would you have an idea if they are also supported along with the vector search, or maybe hybrid, even better?
So if it's a plugin, that would probably be community driven rather than something that we would be dealing with at Elasticsearch. So it's basically community will maintain their own plugins. So it's probably a case that there'll be community members that are maintaining those for subsequent versions. The best kind of advice I'd have is for those, there is a list of plugins on the site, but obviously the other thing is maybe go and check out the GitHub repo for those particular plugins, because they normally specify what are the compatible versions, also what the contribution guidelines are, because they are community maintained. But obviously if that plugin is doing the particular scoring that you want it to do, I would check those and check and see if it does say it's got support for KNN and also later versions in version 8 where the KNN search appears. Does that make sense?
Yeah, thank you.
And thank you for the correction, I appreciate it.
Yeah, hi Kali. Always nice to hear from you.
Thank you.
Looking into the dark future, do we see a possibility of Elastic coming up with their own LLM, tightly coupled with the engine itself, to get over all these performance kind of considerations?
So there is a model that we have called ELSER. Let me bring this up. So this is a retrieval model rather than LLM. So this is the current state of what we have. And basically this kind of is nice because it solves a couple of issues such as vocabulary mismatch because of the expansion of terms. So the way that this works is it takes your query and then it generates all the expanded terms as per the classification in the model. And then it uses those to perform the search. It is a platinum feature. It is a warning. But if you wanted, you can play with it on free trial. But this is kind of the state of what we've got at the moment. In terms of general LLM, I haven't heard of anything about active development of our own LLMs at the moment. It's not something I've actually heard of discussion. What we've been talking about mainly is allowing people to bring LLMs from the community ecosystem using repositories like Hugging Face or their own and uploading them that way and then using them on top of their data set in Elastic, as you kind of saw before. So that's kind of the state of where that is at the moment. But it's something that we're playing with as well. I mean, we've got the assistants that are on beta at the moment, which are for observability and security data sets, and they are basically a large language model for observability and security cases that actually run on top of your data, and you can interact with it and ask questions in a kind of chatbot kind of way. So those are the kind of two kind of positions where we are on LLMs at the moment. But if it does change and we are building our own LLM, I'll definitely let you know.
Thank you.
Thanks.
Thank you.
Lovely. Any more questions for Carly? No? Amazing. Let's thank you, Carly, for...
Thanks, everyone.
Brilliant. So I think we're going to break. I think we're back in here after lunch, so we'll see you all back then.